And to introduce Joel, he graduated in mechanical engineering with specialization in thermofluid dynamics in 2002 in Brazil. An MBA followed in 2015 in a joint educational program between Austria and USA. Joel joined FCT in 2016 and has since then held a number of roles working on projects across more than 70 countries, all related to combustion in energy-intensive industries such as cement, lime, steel, and other minerals. Joel is now CEO of FCT Combustion, a world leader in high-temperature processing plants for heavy industry, and he is based at the European company's headquarters in Vienna, Austria. So, Joel, the virtual floor is yours. Over to you. Thank you very much.
Thank you very much for the nice introduction. Today, I will go a little bit outside the clinker production itself, still in the pilot processing line, but for calcined clay. The idea is just to give an overview about how you can start with calcined clay, either in new equipment, new kiln, new flash calciner, or in an existing line. So first of all, I'd like to paint a picture here so once upon a time, there was a planet called Earth, very green planet. A lot of people started to populate this planet, and today we are 8 billion people. For the next 15 plus years, so until 2050, is expected we are 2 billion more, so coming up to 10 billion people in the planet, which means 1 New York worth of people every month. And it's also expected that by the year 2050, 60% of the infrastructure to be available then is still yet to be built. This means, obviously, that we need more infrastructure, more energy demands, more construction materials, more natural resources in general. And this generates an immense impact on global warming, as discussed previously, right? This is a topic that is much more... a lot in the news today, in the discussions, every type of industries. Does it mean that we are all doomed, that this is the end of the times? Actually, no. If we all do what has to be done, and we have to emphasize the if here because it's a huge point. So we all know this waste hierarchy pyramid. On the top of this pyramid, it's an inverted pyramid. So on the top of the pyramid are the actions that we all can do, and they have more effect on the environment. So first of all, we should try to reduce the use of materials. If we cannot reduce, we should try to reuse them. If we cannot do this reduce and reuse, we should recycle. And in the end, we should repair or recover. Disposing the material should be avoided because this is the worst for the environment. And as I mentioned, to have an impact on the environment, everyone's effort is important, especially on the repair and recover side. The industry's efforts are very much important, and that's what we will talk a little bit more today. So depending on the source that you use, it's expected that it's mentioned that 6 to 8% of all man-made CO2 emissions are coming from cement production. So if we take some data from 2022, we are talking about 1.6 million tons of CO2 emitted in 2022. If we try to divide these 1.6 million in different categories, we can find 3 different categories. So from cement production, one would be related to process emissions in gray, one would be from fuel electricity emissions in light blue, and one transports in dark blue. When we are talking about the fuel and electricity emissions, especially on the fuel side, we can help reducing CO2 with alternative fuels. This will not be the topic of the discussion today. The previous webinar made in March 2024 by us, FCT was present on that as well, in Semtech, March 2024. We discussed in details alternative fuels, so I think if you have any point there, you can take a look at this part of the of this presentation, of this webinar. And in terms of process emissions, CO2 from the process, we can reduce using calcined clay. Part of it can be reduced using calcined clay, and this is the topic of today. So if we want to talk in one slide how to produce calcined clay, this is it. So Using calcined clay as a replacement for clinker has environmental advantages when compared to clinker. Around 30 to 40% of emissions from the raw material are reduced, and also commercial benefits, because the specific consumption to produce calcined clay depends on different conditions, moisture, and so on, but it's between 100 and 400 kilocalories per kilogram lower than producing clinker. The next is how you produce calcined clay. So basically, clays are aluminum silicate oxides that you put through heat, and this will release the hydroxyl part from the crystals in the form of water. And later on, when you take the aluminum silicates without the hydroxyl and you combine with the calcium oxides from the cement, this will produce the strength that you need to replace the clinker. For every clay, there are different phases that the clay goes through when it's being calcined. So first of all, this is a common test that is made for clays, thermogravimetric and differential scanning calorimeter analysis. So here you can see on the x-axis the temperature, and on the vertical axis you have the mass and the energy released by the sample. So here around 100 degrees you have evaporation of moisture, and then in this specific case, between 400 and 800 degrees, you have the activation of the clay. And if you go further, at higher temperatures, you can see that exothermal reaction starts to happen. Is this blue line going up? This means a recrystallization of the clay, and you don't want that. So this reduces the reactivity of the clay. So what is important is to heat the clay up to the end of the activation zone, but preventing the start of the recrystallization. There are different types of clay, three examples here: kaolinite, illite, and montmorillonite. And the activation and the crystallization of the clay happens in different temperatures for each of these clays. And in real life, what we have as well, it's that each clay is a mix of different clays. So you don't have only pure kaolinite. I mean, you have, but it's very unlikely that this pure kaolinite will be available to cement plants. They are used for other more noble uses. And what is important to say here is that every real life clay is different from each other. In a clay project, everything starts, a good project would start with a good characterization of the clay. So first of all, you should have a representative sampling from your quarry. Then you would make some basic tests like XRF, XRD, loss on ignition of this clay. And the objective here is to start with a large number of different types of clay and eliminate step by step the clays that we see that have less potential to bring resistance to the cement later on. So in the next steps, you would make a TGA DCS, that this was the chart I showed in the previous slide, particle size distribution as well. You would then go with this reduced amount of samples again. You would go to a laboratory and try to make a muffle calcination and test the reactivity of the calcined clay. Then you would make a expulsion test to see how are the contaminants in the clay being released and what has to be done in terms of flue gas treatment. And after that, you would go for pilot testing. And at the end of this process, you would have a very good idea. You would be able to design then your plant to receive to produce clay. So as I mentioned, from the top to the bottom, we decrease the number of samples that we are using. So perhaps we start here with 20 different types of clay. At the end, we have for pilot testing perhaps 2, but the results are more detailed as we go down in this pyramid. So this is more or less the way from the quarry passing through the laboratory and then a pilot test. And then obviously there are different possibilities. You can use a new plant or you can modify an existing plant. So if you are talking about a new plant, there are 2 industrial possibilities: a flash calciner that is very similar to a pre-calcining tower in a clinker line, or a rotary kiln that is not exactly, but very similar to a clinker kiln itself. Or we can reuse an existing line and convert it to produce calcined clay. There are some specific points that you have to take care when you are, especially when you are converting an existing line. For example, we are talking here about if the operation would be dedicated for clay, or you want to produce clay for during some months and clinker during some other months. We need to take care about gas velocities at some specific points, like kiln hood, kiln inlet, cooler, and so on. The combustion system has to be checked because most likely in a clay environment, when you're producing clay, the secondary air is much colder than during clinker production. So this has impact on the combustion. So the combustion system itself, the burner, has to be adapted to operate with the clay conditions. And obviously then the fuels that you intend to use, a cooler design, and other plant-specific points. If we just take an example here, so this would be a diagram of a line for producing clay. In this example here, we have only the kiln itself directly. So if we are talking about clay with a high moisture, so we would need to design this kiln with a larger diameter, mainly because of the moisture of the clay. Then would be one single equipment for drying and then calcining. The cooler itself would have somehow would be under-aerated because of the restrictions of the system, how it is designed. We would have one heat source through the burner in the kiln hood, and then all the gases passing through the line would need to be treated against VOC, SOx, NOx, etc. Now, if we, for example, want to improve on this design, we could put a dryer separately, right? So if you are talking about a clay with around 5% moisture, this is not necessary. It still improves the process, but not as much. But if you are talking about 20, 30%, this is a very high improvement. So what happens here is that now we can have a smaller kiln, so CapEx, OpEx lower, because this part of the system is mainly doing the calcination of the product. Then we are talking about a separate equipment for calcining and drying. The ventilation of the cooler is much improved, and as you can see, part of the secondary of the air from the cooler is passing through the kiln, part is going to the dryer, and you have two heat sources: the burner in the kiln and the hot gas generator to increase this tertiary air temperature going to the cooler, to the dryer, and only a small part of the gases are being treated then against NOx, SOx, etc. And this makes the flue gas treatment system much cheaper. Okay, one point that we should also talk when we're producing clay is about color management. So you can see here on the top a raw clay with a brown color. Here a calcined clay using a specific color control method. So the color of the clay itself has no correlation with the cement strength later on, but has a psychological influence in the buyers of this cement. So they don't want to buy a brown cement. The reason here for the brown color is the iron, and when the iron content in the clay is above around 5%, this becomes a concern for something has to be done to control the color. Below this value, most likely the clay will stay will be converted to gray color by itself. Above this value, you need to take care. Basically, what's happening is that we have iron in the clay under the form of hematite, but this hematite can be converted to magnetite. Hematite is brown, magnetite is gray. So if we look here in this diagram, we can see this is doing calcination in the presence of oxygen on the left, in the absence of oxygen on the right. We can see that as the temperature rises, the clay becomes gray because the hematite is becoming magnetite, but then we start cooling down the clay, again, in presence of oxygen, in absence of oxygen, we can see that it goes from the gray color on the top to the red color at the bottom in case we have presence of oxygen. So there are different ways to control the color based on that. One is to reduce the oxygen, because if we have lower oxygen, we go more towards the gray color. Second would be quenching, so to reduce the temperature very fast of the clay. This has limited use and also increases a lot the cost, the OpEx, because you're not recovering energy from the process. And the third method, it's a method patented by FCT. Basically, we use some source some material that is readily available on site to capture the iron and prevent the iron to go back to hematite. We can discuss this more in details. I have a video here of a test that we made. So this is the clay. You can see a very red color we put into our pilot kiln that we have. This kiln can process up to 1 ton per hour clay. And perhaps I speed up here a little bit. You can see the burner. In this case, is a burner, a natural gas burner. Here is the clay, the calcined clay. And at the bottom, you can see the clay coming out with this inorganic modifier process that we have coming completely gray. So you can see here, just to illustrate the color of the rock clay, the calcined clay on the top right, and the calcined clay mixed, 25% calcined clay, 75% cement mixed here. Obviously, this is also not only in the pilot. So this is, you can see here, so I can stop these 2 videos, but you can see here a clay with 15% iron from a client of us. So this is a real kiln. And here you can see the color of the clay coming out of this kiln. So just to illustrate here, so we can see a rock clay on the left, calcined clay on the right. In this case, without the inorganic modifier, so it would become brown. And the same clay, using the inorganic modifier, you can see that this becomes much more on the gray color. And an additional advantage is that you start forming these small granules. And this is good later on for the operation of the cooler, for recovering heat from this clay and so on. Obviously, we can use alternative fuels to reduce the CO2 footprint even further, but different solutions require, there are different requirements. So we have different requirements for a flash calciner, we have different requirements for rotary kiln. So it's important to know which type of equipment you are using, which type of alternative fuel you are using, liquid alternative fuels, solid alternative fuels, and the characteristics of this fuel, the temperatures in the process where you intend to inject the alternative fuels, and the substitution levels that you want to achieve, obviously also very important, and the combustion time available inside the equipment. So these all, and if there are any color control requirements for your process, for your specific type of clay. If we are talking about a flash calciner, I think there are different options. So first of all, the flash calciner has a very short residence time. And this is the main reason why we need to make a combustion in a separate equipment. So we can have, for example, different types of hot gas generators. You can see here on the right side, 2 types of hot gas generators for alternative fuels. One is a fluidized bed, one is a grate hot gas generator, and they would produce hot gases that would be then injected into the flash calciner to make the calcination of the clay. And if you want to go to higher substitution rates, up to 100% even, then we would use a gasifier. This gasifier would produce a syngas, a synthetic gas coming from the alternative fuel, and this syngas would be then used as fuel for the flash calciner itself. In terms of the kiln, rotary kiln, there are small differences. So the residence time inside the kiln is longer than in the flash calciner, but as I mentioned, the secondary air, the environment inside the kiln is much colder than during clinker production. So I think there are two main ways to use alternative fuel in a rotary kiln. One would be to use a state-of-the-art alternative fuel burner. So again, I recommend you to watch the last webinar in March this year. We made a detailed presentation about firing alternative fuels in the kiln. And also, but this only allows you to achieve a certain substitution rate. If you want to pass that substitution rate level, you need to use a gasifier again, produce a syngas, and then use the syngas as the main fuel for this burner. I think these were the main points I would like to talk. So I just go very quick now because my time is ending about the company, FCT. FCT, we are working in 3 different branches. So combustion, ACTEC, making online analysis for process control, and FCT Flames that we make entertainment flames, for example, for the Olympic Games. So I'm sure that all of you already saw FCT without knowing that you saw it. We have 5 main offices in Australia, China, Austria, USA, and Brazil. The company has now 45 years. Worldwide presence, more than 1,000 combustion systems installed. We are working mainly in cement and iron ore industries, but we also are working other industries, other mineral industries. And this possibility, this allows us to bring one technology from one industry to the other. When we started our company, we were only dealing with rotary kiln burners, but today we can help the plants, our clients in the whole plant. And from our main products, we are talking about rotary kiln burners, hot gas generator, calcining systems, fuel handling systems, panel management systems, as well as services such as CFD. We have a group of people inside our company doing CFD 100% of the time, fuel conversion systems, process auditing, functional safety services, and so on. We have, as I mentioned, 2 pilot plants. So one would be for clay up to 1 ton per hour. A second one, a flash calciner up to 50 kilos per hour. Here are just some pictures of recent projects that we delivered. Some of our clients. And at the end, I just want to finish the presentation saying that the nature is making calcined clay for a millennia. And FCT is making calcined clay for 45 years. So this gentleman here on the left of this picture is working with this since the 80s. Thank you very much. Here are some contacts. If you have questions, I'm open to answer them. Otherwise, you can contact me later on as well.
Thank you, Joel. As I can see, for the many questions coming in, there's huge interest in this area of calcined clays. And clearly it is one with growing potential, but yet there's a lot of learning in both the raw materials and in the processing required. Just to take a few of the questions, can you use a clay with 20% kaolin and 20% montmorillinite?
Yes, so that's always a question that we get. So which one is the best clay? Ideally, the best clay is the clay that you have available near your plant, right? So you don't want to transport the clay because this inviabilizes the project. So that's why we always recommend to take the clay and make a test on it. So these tests, as I mentioned, this pyramid, this inverted pyramid from the beginning of the presentation, perhaps I can find it quickly here. They don't add, they are cheaper, very cheap tests that you can make at the beginning of the project, and then you can eliminate some clays or at least select the best clays you have available near your plant. So each clay is possible to be used. It's just a question of how reactive they will become and how much you can how much you can replace the clinker by this clay. So better quality clays you can use more, lower quality clays you can use less, but in any case you can use them.
Is there in general some parts of the world where these clays are more available and others less available?
Yes. So there are geological maps that show you concentrations of different clays in general, right? So clay is a very heterogeneous material. So if you go in the same quarry, some meters to the right, some meters to the left, you have different clays. But as a general information, there are geological maps that can show you this. The concentration of different clays in different parts of the world. But the best is if you take some sampling from your available clay, quarry.
Yeah. And what are typical figures for the heat consumption and electrical energy consumption compared to traditional process?
Yeah, so these are much lower than a clinker production. It depends a lot on the characteristics of the clay. Sorry if I come back always to this, but at the end of the day, everything depends on the clay. So if we are talking about a 30–40% moisture clay, most of the energy used during the calcination is not to calcine, is to dry the clay, right? So there's a huge difference between a clay with 5% moisture and a clay with 30–40% moisture. So we are talking, the calcination reaction itself uses only around 160 kilocalories per kilo, right? All the rest that we see, a typical clay line would be perhaps 400–450 kilocalories per kilo. And this would be losses with hot gases, losses with material temperature, drying, and so on and so on. So it depends on the clay. And the same for the electricity. I think it depends if you are talking about a rotary kiln or a flash calciner. And it depends as well if you need to grind the clay or not. Most of the clays are very fine already by nature. They just have bigger particles because of the moisture. But when you dry them and tumble them around in the kiln, they become a very fine material itself. So you don't need to grind them. But in some cases, yes, you need to do it. And this adds additional electrical efforts there for the grinding. So if there is more specific clay that anybody has and wants to discuss, please contact me and we can go through this more in details.
Yeah, obviously it depends in each case on the clays available and the qualities of them before you actually go into designing the process most suitable for your raw materials.
Correct.
Question, what is the largest such unit in operation, and are there many around the world so far?
I think there are some in the world. I would guess today, if we are talking about converted kilns and new specific lines that are designed for calcined clay, I would say something around 20-25 lines. And I'm not aware about the biggest line. I would say something around 1,500 kilos, 1,500 tons per day, something in that range. I would say so.
I see. Yeah. Okay. I think it's really opening up a new train of thought and a new way of producing clinker ultimately, and calcined clay is a very important part of the solution where the clays are available around the world for the industry. So your presentation, Joel, has been most interesting and most useful, and I think will again open up the conversation afterwards, where I'm sure you'll welcome questions and answers, questions from people that wish to pursue and actually
they can just contact
trials.
me, no problem.
Yeah, great. Thank you very much, Joel.
Thank you.